Hello everyone. In the last class, we discussed about public key cryptography. We understood what is the need of getting two keys, one for encryption and one for decryption, which helps in having a secure, I would say, communication, so that they don't have to transfer the private key associated, and you can make the overall communication more secure. So the main intent of a public key cryptography is that if Alice wants to send any message to Bob, would be generating two keys. One is the public key, so that it can share it with the person, which is Alice over here, and one is the private key, which he will keep it with him, so that nobody is able to access that. And that public key would be used by Alice in order to encrypt the message using that public key, and so that it generates the ciphertext, and ciphertext which is given back to the Bob can apply the private key associated with the ciphertext. He can apply the decryption algorithm on this private key on this ciphertext in order to generate the message over here. And that is what we had discussed in the last class. The very first public key cryptography system which came into picture was called as Knapsack, and that was the algorithm associated with Knapsack algorithm, where you generate I would say public private key pairs. And let's first understand what is a knapsack initially. Knapsack is a collection of set, or a collection, you can say it's a collection of numbers or anything, and you have to get a message out of it. Let me try to explain you. So let us suppose that you go to Walmart and you have to buy 950 grams of apples. And once you go into the store, you find 110 grams of apple, you get 125, you have a set of 150, you have a set of 256, and so on. In the end, you want to get a total of 950 grams. So how would you, and these are some, I would say some values, which is A1, A2, A3, A4. So in the end, what you have to do is you have to have the xi into ai, the summation of I is equals to 1 to n, where n could be from 110, 125, such that an x could be a vector which can include either 0 and 1, such that the value is equals to 950. In the end, you want to get 950 over here. Let me give you another example. Let's suppose that you have a set of some numbers. So let's suppose that you have a set of 1, 6, 8, 15 and 24. What are these? This is A1, A2, A3, A4 and A5. And if I ask you that you have to generate a number which is 30 from this set, which is 1, 6, 8, 15 and 24. So what you would be doing, one way to generate that particular number to get 30 is if I multiply 1 by 1, so it would be 1, plus 6 into 1 would be 6, plus 8 into 1, so it would be total 9 plus 6, which is 15, plus this 15 would give me a total of 30 over here. So this would be 1, this would be 1, this would be 1, this would be 1, this would be 0. So then the number that the xi values would be, this is xi and these are ai's. So xi that you would be getting is 1, 1, 1, total 4, 1 and 0. Let's suppose if I ask you to generate a number 40. In that particular case, if you do some kind of combination and permutation, once again, a key like all these ai's can have a total of 2 raised to the power of n combinations. So if it is 5, a set of 5 numbers, it would be 2 raised to the power of 5 combinations that you can generate: 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0 and all those. So given the size of the set, those many subset could be generated. So for instance, for getting 40, for instance, what you can do is, if you add 1 plus 15 plus 24, which would give you 40 among this set of 1, 6, 8, 15 and 24, which means 6 and 8 would be 0, but 1, 15 and 24 would be equal to 1. So the set that you would be getting is, the plain text that you would be using is 1, 0, 0, 1, 1. Let me give you another example. Let us suppose if you have to get 22. So in order to get 22, if you add 1 plus 6 plus 15, you would get 22, which means that 1 you can make it as 1, 6 also you will make it as 1, 8 would you make as 0, 15 you would make as 1, and 24 you can make it as 0. So this would be the plain text, or I would say these are the values of xi that you would be getting. And it depends upon any value that you have to generate over here. So the problem statement over here is, what you need to do is, let me present this. And this is what is termed as a subset sum problem. What is a subset sum problem? Subset sum problem says that given a set of a1, a2, an, and a sum value that you have to generate, you have to get xi's, the values of xi's, such that if you multiply a1 with x1 plus a2 plus x3, so on with an with xn, you would get the sum value that you have to generate. Remembering that xi could be a vector only containing zeros and ones. So this is the subset sum problem that is being used. An easy solution for this subset sum problem is, arrange the numbers or the set in a super increasing sequence. What is a super increasing sequence? Super increasing sequence means a1, a2, a1 should be a1 should be less than a2, a2 should be less than a3, and so on till all the numbers are generated. Or you can say a2 should be greater than a1, a3 should be greater than a1 plus a2, a4 should be greater than a1 plus a2 plus a3, or you can say ai should be greater than a1 plus a2 till ai minus 1. Or you can generalize it with the help of n numbers. So an would be greater than a1 plus a2 till an minus 1. This is a super increasing sequence. And this is computationally feasible problem if we take, as I said, the sequence as a super increasing function. So as I said, and this is an easy knapsack problem or an easy knapsack algorithm. A simple solution for getting the values of xi would be, for instance, if you run the loop for the value of I and running from n down to 1. So you have to start from the last number till you reach the first number. You first check whether s, the value that s you want to compute, is greater than ai, which is that value which is n. If that is greater than n, what you do is you assign xi is equals to 1 and you compute the value of s, which is s is equals to s minus ai. So I'll give you certain examples so that you understand this. But if that is greater than s is greater than ai, you will assign xi as 1. You will find the difference of s minus ai. Otherwise, you will just assign xi is equals to 0. And this program will run until and unless you reach the final number, which is 1, which is the end of the overall loop. That's the one thing. Once you have computed these values of a1, a2 to an, with the assignment of xi's operation, if some value is become 0 at the end, you have to calculate the sum. If s becomes 0, then you will create that particular vector as x is equals to x1, x2 till xn. Otherwise, there would be no solution in that particular case. This is a easy knapsack algorithm. Why it is called as easy knapsack algorithm, I'll try to make you understand, but let me give you an example. So let me open a whiteboard to help you understand. Okay, so now there is Alice and there is Bob. Okay, Alice and Bob wants to communicate with each other, where Alice has to send some message to Bob. So if since Bob has to get like Alice has to send a message to Bob, Bob would be generating a public key and a private key over here. Okay. But I will help you understand this. But here what Bob will do, Bob would get a series of numbers. Okay, so these numbers, let me give you certain numbers: 171, 197, 459, and 1191 and 2410. Okay, according to the algorithm that I was saying, you have to have some value that you have to create, and let's suppose the Alice wants to send a message. Let's suppose this xi value is 01011. Okay, so what Bob will do, Bob, since this is in the form of super increasing sequence, 171 is less than 197 and so on, Bob will make this sequence of number available to Alice. Alice on the other side, what it will do, it will multiply 0 into 171. So it would be summation of AI and xi would give you the sum value over here, which is, once you will calculate this, the value that you would get would be 3798. Alice, once computes this number, would send this 3798 to Bob. So Bob, on receiving this 3798, what it will do, using this algorithm that I was saying, what he will do, he will calculate S is equals to S minus 2410, because S value is 3798 is greater than 2410. So the value that it would get would be 1388, and x4 value would be equal to 1 in this, sorry, x5 would be equal to 1 in this case. Okay, then it will again solve this. Next time it will calculate 1388 minus 1191. Once again x4 would be calculated, would be 1, and x3 would be equal to 0, x2 would be equal to 1, and x1 equals to 0. So if you will do this particular value, all this value would be 01011. This is how he would be able to get the plain text over here, which is 01011. Okay, so the algorithm that I just explained to you, if you will solve this, you will get these values. This is what is termed as easy knapsack problem. Why it is easy knapsack problem? Because, for instance, there is third person called Oscar. If Oscar knows this public key which Bob was sending, which was a series of super increasing sequence, and Alice, it computes this value, sends this value which is 3798, Oscar can apply the similar kind of algorithm in order to get the plain text over here. So this is termed as a easy knapsack problem. So we need to have a better solution with respect to this. So one way to get a better solution is, why don't we have, instead of super increasing numbers, why don't we create some random data instead of sending a super increasing number? And if I send this some random data, Alice would still be applying the plain text by multiplying this plain text with the random set, and once they say the Alice sends that particular random text, can I still apply some kind of algorithm to get the sequence over here? How would I be able to do it? Using the modulus operation. So remember, we talked about modular, inverse, and how to compute the GCD of two numbers. So this is what would be happening for making this particular problem as a hard problem, so that the person would not be able to access what Alice and Bob are communicating. So there is this Alice and Bob. Let's suppose that Alice has to send some message. What Bob will do, this is the setup phase. This is what the Bob will do. Bob will first calculate A prime, which is a set of some super increasing numbers, which is A11, A21, and an1. Once again, this is secret key. This is what is termed as the secret key or the private key for Bob. Okay, so Bob would be having a super increasing sequence of numbers, and this would be only and only known to Bob. Next, what Bob will do, Bob will have two numbers, which is M and W. Okay, where M is greater than equal to the summation of I is equals to 1 to n of AI, such that this M value would be always and always greater than the summation of I is equals to 1 to n greater than I. That's the first thing. Other thing, how does the Bob calculate W is by calculating a number which is GCD of M and W should be equal to 1. Once we get this, which means that if GCD of M and W is 1, remember that if GCD of two numbers is equal to 1, then modular inverse exists, such that if you get modular inverse was something like that, W into W inverse would be giving you, under modulus operation, M should be equal to 1 because GCD of M and W is equals to 1. The third thing is that once it has calculated this M and W, what it will do, it will calculate AI, and AI is nothing but multiplication of W into this AI or AI prime under modulus M operation in order to generate this AI, and this AI would be the public key that it would make Alice make it to Alice, and Alice would be able to access it. Once again, this AI would not be a super increasing values because here you are multiplying W with AI in order to get that particular number. So we are able to solve this particular problem of not sending a super increasing sequence but a random amount of sequence that would be given to Alice. Alice, on the other hand, what it would be having, Alice would be having a plain text which is in the form of 0 and 1. This would be n bits, and the cipher text that we would be getting would be any number which is 0 to n minus 1, and xi, or x value that we would be getting, the total value is that in the end we would be having a dash m and W. This is only known to the Bob, and we would be calculating A over here using this particular algorithm, overall algorithm. And this A dash M and W becomes the private key, and this A is known as the public key over here. Okay, so now what Alice would do, Alice would apply the encryption algorithm and encryption or under this A, which is the key over here, on x1 to xn, where x1 to xn is the plain text of the Alice, such that summation, this is equal, the summation, the set value, S value or a knapsack value is I is equals to 1 to n xi into AI. This is what would be the encryption algorithm. Once Alice has found the encryption algorithm, this or this value of S, he would be sending it to Bob, and Bob, once receiving this subset value which is S, what Bob will be doing once it has received S, since GCD of M and W was equals to 1, which means multiplicative inverse exists for that particular number. So S, we know S that we calculated was the summation of xi into AI. If we multiply, this S value with the multiplicative inverse of W, which is W inverse S modulus M, this would give us S prime. Okay, S prime is nothing but multiplication of W inverse, because we multiply it with W inverse into what is S? S is xi into AI, summation of xi into AI, which is W inverse x1 a1 plus x2 a2 such that plus xn an. And if you will multiply w inverse x1 a1 plus w inverse x2 a2 and so on, in the end we would be getting a1 prime, this is that particular number, that was the first number, into x1 plus a2 prime x2 plus an prime xn. So finally, in the end, we would be able to get the values of x1, x2, xn, and we would be getting the values of a1, a prime, a2, and this was already known to the person, because if you recall what I was saying, w inverse of ai would be equal to ai prime, because GCD of because if you recall, we had discussed that ai is equals to w into a inverse modulus m, which means a into a dash prime, which means that if I multiply it with w inverse, this value would be equal to w inverse ai equals to a prime. Okay, if I multiply it with w inverse, this is what we would be getting at the end. So this is what is termed as a knapsack problem, and this would be able to solve so that Oscar is not able to access the example. So let me give you an example. This was all with respect to maths, some mathematics associated with it, but let me give you an example to help you understand this problem. So let us suppose once again we have Alice and we have Bob, and this time I'll give you certain numbers over here. So Bob has a set of a prime. So that was the first step. If you recall, I was saying that let's have a super increasing numbers, and this super increasing sequence would be considered as the private key. So let us suppose we have a sequence of 2, 5, 9, 21, 45, 103, 215, 450 and 946. Okay, this is a private key to Bob. Bob generates a super increasing sequence of these numbers, which is only and only known to Bob. But Bob, if Bob will send this numbers in a super increasing sequence, you recall that Oscar would be able to get that particular sequence, which is the plain text, because he has this a prime, and it can do the summation value, which is xi's and ai's, in order to get that particular number. So that was not a feasible approach. That's the reason we have to create an a prime or a value of a sequence such that it is not super increasing in nature. So the second step, if you recall, I said Bob has to have two numbers, which is m and w, such that GCD of m comma w is equals to 1. So GCD of m comma w equals to 0 means we have to get two numbers. So let us suppose I get m is 2003. That's what, if I add all of them, the summation of all of this number should be greater than m should be greater than this number. So if I add all of them, I would be let me show that to you. So I take a number, if I multiply all of them, I get a number which is if I add all of them, I get a number 1796. I am choosing a number which is m, which is greater than 1796, which is 2003. Now what I am doing, I also want to have w over here, another number, such that the GCD of m and w would be equal to 1. So let us suppose that I get a number 1289. So which means if I calculate the greatest common divisor of 2003 and 1289, and you can use Euclidean algorithm or anything, you would get the GCD as 1. So that was the second step. The third step that I do is what I'll do, I'll be multiplying w and ai under modulus m operation in order to get a sequence of numbers. So if I'll do this, which means if I do 1289, which is the w over here, 1289 into 2, so 1289 into 2 under modulus 2003 operation. If I'll do this, let me open the calculator. 1 second. So 1289 into 2 gives you 2578, and if I do this modular operation, we would be getting 575. So I would be getting the first number as 575. Again, what I'll do, I'll multiply 1289 into 5 modulus 2003. I will get another number which is 436. Then once again it would be 1586, and you can solve it. 1030, then 1921, then 569, then 721, then 1183, and then 1570. This sequence, if you see, this is not super increasing in nature. It's not, because the numbers are arbitrarily arranged. This would be made as the public key. So now Bob would be sending this particular public key to Alice. So this is the AIs. This was AI prime over here. That was the private key over here. So now we get two keys over here. One is public key, one is private key. Public key over here is not in super increasing in sequence, but private key is over here is a super increasing number. Alice, on getting this number, let us suppose Alice wants to send a message 1011001111. So what it will do is it will calculate the sum, which is summation of I is equals to 1 to n xi into ai, which is this ai would be 575 into 1 plus 0 into 436 plus 1 into 1586 plus 1 into 1030 plus 0 into 1921. So this is what 1011001111. If it will do this, it will get 6665. This 6665, it will, Alice will send it to Bob. So this is now encrypted. This encryption would be provided to Bob. Bob, on receiving this number, let us suppose Oscar also comes in and Oscar tries to access this number. Oscar, what it has the public key, which is this key, and the summation value, which is 665. But if once it will do this calculation, he would not be able to get the plain text over here, because it's not in super increasing in sequence. Bob, on receiving it, what Bob will be doing, if you recall what I was saying, Bob will be doing, since GCD of M and W was equal to 1, which means multiplicative inverse exists, which means 1289, what I should multiply it with 129 under modulus 2003 would give me 1. And we can apply different kinds of algorithm. If you recall, we can use Euclidean, extended Euclidean algorithm, you can use Fermat algorithm, or you can use a brute force algorithm where you again and again multiply this. If you do not recall, I would encourage you to go back and see how you can calculate the modular inverse. But if I can write this, or you can do it mathematically, but if it is 12892003, the modular inverse of this number would be 317. And once I get that particular number, which is, if I multiply 1289 with 317 under modulus 2003, I would get the value as 1 over here. So which means that now what I have to do, I have to multiply this 317, which was W inverse, with the S under modulus M operation. So what I'll do, I will be doing W inverse, which is 317 into S, which was sent, which was 6665 modulus 2003. If I'll solve this, I would get the value as 1643. This 1643 is the text that I would be using in order to get the value of xi's and ai's. So this S prime that I got, I would be getting is 1643, and then once again I'll apply this algorithm of I is equals to 1 to n xi into ai, which is the same algorithm that I showed you, because So once we have got this S prime, what Bob would be doing, Bob would, since he has its own private key, he can apply the same algorithm that I had discussed initially, that if S prime is greater than the AI, then we would be doing 1643 minus 946. We will calculate the new sum, and xi would be equals to 1 in this case, and similarly this process will continue until we get that particular sequence of xi would be once we will do this overall algorithm, we would be getting 1011001111. So this would be known only and only to Bob. Oscar in between, even though he has this public key as well as this summation S, which is 6665, he would not be able to recover that particular value, which is the plain text, because the sequence is not in super increasing in nature. But Bob, since it has its own private key, he would be able to decrypt this particular message, and this is what is termed as knapsack problem. And this was the first public key cryptography algorithm where Bob is able to generate, with the help of the known values, which is M, W and its private key, a public key that he transmit it to the other person. Alice, on the other hand, applies some kind of algorithm to encrypt that message. Attacker would not be able to access. Bob, on receiving this, would be able to decrypt it because it has its own private key over here. In the next class, we'll discuss about RSA algorithm.